Hello everyone, this is Bolloji Vashishta from Aerobee section. Today I am going to explain about Laplace transform in electrical circuits. Laplace transform in electrical circuits. The analysis of electrical circuits and solution of linear differential equation is simplified by use of Laplace transform. In actual physics system, the Laplace transform can be interpreted as the transformation from the time domain, where input and output are functions of time, to the frequency in the domain, where input and output are functions of complex angular frequency. The circuit analysis example: in an initial current, KCL, KVL, and branch relation yield minus U plus Li plus Y equal to 0 and Y equal to R1. Here, Y is the potential difference, R is the resistance, L is the light bulb, I is the current passing through it, U is the power source. And to the Laplace transform to get minus U plus L of Si minus I of 0 plus Y equal to 0, Y equal to Ri. For the Y to get Y equal to U plus Li of 0 by 1 plus SL by R plus 1 by 1 plus SL by R into U plus L by 1 plus SL by R I into 0. Here in the domain, in the time domain, Y of t equal to 1 by t into integration of 0 to t e power pi by t U of t minus pi d pi plus Ri into 0 e power minus t by t, where t is equal to L by R, two terms in Y or Y. First term correspond to solution with 0 initial condition. First term is convolution of source with a function. Second term corresponds to solution with 0 source. And we'll see the general properties. Analysis of general LCR circuits. Consider a circuit with n nodes and p branches containing independent sources, linear element, resistors, ohms, and inductors and capacitors. Such a circuit is described by three sets of equations: KCL, KVL, branch relations. KCL is AI into t equal to 0, KVL is equal to V of t equal to A power t into ET, and branch relations where A belongs to R into a whole power n minus 1 into B is a reduced node incident matrix. I belongs to R power B is the vector of branch current, and V belongs to R power B is the vector of branch voltage. E belongs to R power n minus 1 is the vector of node potentials. And in branch relations, independent voltage V of k of t equal to U of k of t, resistor V of k equal to Rik, capacitor Ik is equal to CV dash k, inductor Vk is equal to Lik, and VCVS is equal to Vk is equal to AVJ. Thus, circuit equations are a set of 2b plus n minus 1 linear algebraic or differential equations 2b plus n minus 1 variables. Laplace transform of circuit equations. Most of the equations are same. Example: KCL, KVL, A equal to 0, V equal to A power t into E. Independent sources Vk equal to Uk becomes Vk is equal to Uk. Linear static branch relations Eg equal to Vk into where KCL independent source and the differential equations become algebraic equation. Capacitor Ik is equal to SCVK minus CVK of 0. Inductor Vk is equal to SL of k minus Li of k equal to 0. Thus, in frequency domain, circuit equations are set of 2b plus n minus 1 algebraic equations in variables. Thus, LCR circuits can be solved exactly like a static circuits. Expect all variables are Laplace transforms, not real numbers. Capacitor inductors have branch relations. Ik is equal to SCVK minus CVK of 0. Vk is equal to SLIK minus Li of k equal to 0. Interpretation: an inductor is like a resistance. SL of A is in a series and with an independent voltage source Li of k. The capacitor is like resistance in parallel with an independent current source CV of k equal to 0. The resistance are called impedances. These sources are impulses in the time domain which set up with the initial condition. Impedance and admittance. Circuit elements are devices with voltage V, current I. The relation V of S equal to ZS IS is called an impedance description of the device. Z is called the domain impedance of the device in the time domain. V and I are related by convolution. And similarly, I of S equal to Y of S into V of S is called admittance description. Y of Y equal to 1 by Z. Examples. A resistor has an impedance R. An inductor with zero initial current has impedance Z of S is equal to SL. Admittance I of S by L. A capacitor with zero initial voltage has impedance Z of S equal to 1 by SC. Admittance S of C. Impedance is triple S analysis with the phasors. Resistor V equal to Ri. Inductor V equal to J omega Li. Capacitor V equal to I into J by omega C I. The domain and phasor impedance agree for S equal to J omega but are not same. We can express the branch relation as MSI into NS Vs US plus U of S plus W, where U is the independence of W includes the term associated with initial condition. MNN gives the impedance and admittance of the branches. For example, if a branch 13 is an inductor, SL by 13 of S plus minus 1 into V of 13 of S equal to Li 13 of 3. We can write the circuit equation as one big matrix equation A 0 0 0 I minus A M of S N of S equal to 0, where hence I of S V of S and E of S T is taken as A 0 0 0 I minus A power T M of S N of S 0. This gives an explicit solution of the circuit. These equations are identical to those for a linear static circuit. Except instead of real numbers, we have Laplace transform, that is complex value function of S. Hence, much of it exists in this case. Let us express a solution as I of t, V of t, and E of t is equal to L inverse of A 0 0 0 1 minus A power t, M of S, N of S 0, and plus L inverse of A 0 0 0 I minus A power t, M of S, N of S equal to 0. The circuit response is equal to the natural response, that is solution with independent source of, plus the forced response, that is solution with zero initial conditions. The forced response is linear in U of S, that is the independent source signal. The natural response is linear in W, that is the inductor and capacitor initial conditions. And back coming to an example like initial current I of 0, natural responses set source to 0, get LR circuit with solution. Y of NOI of t is equal to Ri of 0 e power minus t by t. T is equal to L by R. Forced response assumes 0 initial current, replace inductor with impedance Z equal to SL. By voltage divider rule, Y of FRS is equal to U of R by R plus SL. As we are simple resistors, Y of FRS is equal to L inverse of R by R plus SL into U. That is, Y of FRC of t equal to 1 by t into integration of 0 to t e power minus pi by t, U of t minus pi d pi. To altogether, the voltage is Y of t is equal to Y of NAT of t plus Y of FRC of t, and the circuit analysis with the impedances. For a circuit with linear static elements, resistor of amps, independent sources, elements described by impedances, inductors, and capacitor with zero initial conditions. We can manipulate Laplace transform of voltage, currents, impedances as there were real constants, voltage, currents, and resistance respectively. Reason, they both satisfy same equations. Example, series parallel combination, voltage and current divider rule, Thevenin Norton equivalent nodal analysis. Coming to an example where we have 4 ohms of 4 heads of light and 1 ohm of resistor and a 3 ohm of resistor, where input I of 2F. Let us find the impedance Z is equal to V by N. By series and parallel combination rule. Zn is equal to 1 by 2s plus 1 by 4s plus 3 is equal to 1 by 2s plus 4s by 1 plus 4s plus 3. We have V of n is equal to 1 by 2s plus 4s by 1 plus 4s plus 3 into L into S. Provided the capacitor and inductor have zero initial conditions. Example of nodal analysis. Nodal equations are G equal to I into SRC, where ISRC is total of current sources flowing into nodes. GII is the sum of admittance tied to node I. G of Ij is minus the sum of all admittance between a node I and J. For the example, we have I plus 2s plus 1 by 3 minus 2s plus 1 by 3 En of S minus 2s plus 1 by 3 1 by 3 plus 2s plus 1 by 4 plus 1 by 5 where Es of 2 equal to 0. So the Thevenin equivalent of a Laplace transform can be determined as the voltage source is 1 by S minus 1 by S plus 1, that is equal to 1 by S into S plus 1 in S domain. Thevenin voltage in an open circuit, that is VTH is equal to 1 by S of S plus 1, 1 by 1 plus 2S. Thevenin impedance is impedance looking into terminal with the sources of Z is equal to 1 by 2, 1 double dash 2S, that is equal to 2S by 1 plus 2S. The Thevenin circuit can be determined as 1 by S of S plus 1 into 1 plus 2S. SDH is equal to 2S by 1 plus 2S. Natural frequency and stability. We say circuit is stable if its natural response, this case, that is converges to 0 as t is infinity for all initial conditions. In this case, the circuit forgets its initial condition as t increases, the natural response contributes less and less to the solution as t increases. That is, y of t is y of FRS as t is greater than t belongs to infinitive. Circuit is stable when poles of natural responses called natural frequencies have negative real parts. They are given as A000I minus A power t, that of ms of n, m of s, n of s 0. So this is all about the Laplace transform in electrical circuit. Hope you all understood. Thank you.